Welcome back to Wondermass, the social science show. Today we are solving the birthday paradox, and along the way we're going to learn a powerful, flexible and intuitive approach to solving any probability problem that is of relevance to social science. What you're about to see was recorded at Nottingham University Business School, and a big thank you to them for letting us use this clip. In the clip I'm using the software R, and if you want to play along at home I'll give you the download link in the description below. Enjoy. So what we're going to do is we are going to take what might be called an observational approach to probability. You might also come across this idea of a frequentist approach to probability. Let's not get into all of this too much, but what we're going to consider is an analytical approach versus an observational approach. And we are going to take the observational approach. So first of all, what is the analytical approach? The analytical approach just means mathematical, the mathematical approach. To analyze the thing with theory and with mathematics. So if we consider a very common probability situation, a probability problem, rolling a die, and from now on I'm just going to call it a dice. I know that's incorrect, but I'll just call it a dice. So rolling a dice. If we ask the question, what is the probability of rolling an odd number on the dice? The analytical approach is to count the number of faces on the dice. There are 6. To count the number of faces that have an odd number. So that's 3. The odd numbers are 1, 3, and 5. And then say, let's assume that the dice is fair. We've got 3 odd numbers out of 6, 3 out of 6. The probability of rolling an odd number is a half, 3 divided by 6. So that's the analytical approach. And for a lot of people, that approach gets extremely complicated. So when you start dealing with the sort of problems that we had on the screen before, a lot of people find it challenging to use an analytical approach, and I certainly do. I wouldn't attempt to answer any of those questions actually with an analytical approach. The alternative way, this observational approach to probability, is to roll the dice and to observe what happens. So to take an observational approach to estimating the probability of getting an odd number, you pick up the dice and you roll it 100 times. And you count the number of times that you get an odd number. And there would be roughly 50. It won't be exactly, but it'll be roughly 50. And let's say it's 42, 45, 47, something like that. Then we would say that the probability is 47 divided by 100 because we rolled it 100 times. Now that will give you an estimate of the probability. It won't give you the actual probability, but you see, the thing is, there are a number of philosophies of probability and statistics, and we are not committed to one. So the observational approach to give an estimate is perfectly valid, and that's the approach that we're going to take. So what are we going to do? Well, we're going to roll the dice inside a computer. That's our approach. So what we can do is we can program a situation, a scenario, whatever you want to call it. We're actually going to call it a story. But a story is just the situation, and with the dice example, the story is you pick up the dice and you roll it. That's it. That's the story. And we are going to code that inside a computer. And then we're going to say to the computer, right, do that 100 times. And count as you go the number of times that we get whatever it is that we decide we're looking for. So with the dice roll, it's an odd number. But with these other things, we'll be looking for other measures of success. And that's it. So as long as we can code the story, and that's going to be the complicated bit, as long as we can code the story, we can master extremely complex situations and scenarios. And in actual fact, I would say that we can handle them much better than with the analytical approach. Because, for example, maybe the dice isn't fair. Maybe the dice is a wee bit wonky. And as soon as you introduce stuff like that, the analytical approach, the complexity of the analytical approach magnifies. And we will look at examples of this as we go. So what we're going to do is we're going to tell the story. Tell the, oh blimey, S-T-O-R-Y. Tell the story. And that's tell the story once. Now I'm going to eventually copy paste this into R, so I will put a hash before the English bits. And the hash just says to the computer, that's not code. So anything beside a hash, it isn't going to run inside the computer. But in a minute, I'm going to be copy pasting this into R to run it. So I don't want to have English words in the middle of it getting mixed up. If you want to know the fancy term, that's a comment. It's a comment in the code. So tell the story once. At the end of the story, we're going to have to decide, do we want to count something? Is there a success that we need to count? So let's say, is there a success we need to count? So in the dice example, that is, do we get an odd number? That's what that bit means. Is there a success? Is there a situation, an outcome? Is there an outcome that we want to count? And if so, then count it. And that's it. And then all we need to do is up here, if I can find my hash, is we start a loop. And down here, we end loop. Okay? How many times do we loop? Well, we'll worry about that later. Don't worry about that for now. Then after the loop, we just have to calculate or estimate this p, so the probability. So calc probability. Now you'll notice I've left some space at the top because there's some extra stuff that we might need up here. Some extra bits and bobs. So what might we need up here? Well, we might want to specify the number of times we loop. We might also need to specify, if we take our analogy, if we're rolling a dice 100 times, we maybe don't want to be counting up to 50 because we might lose our place. So we might need a notepad and a piece of paper to write down the results. So up here, we might need to get a notepad to write down the results. And a pen and other bits and bobs like that. Now, inside the computer, the fancy way of doing that is we need to organize the memory. Organize the memory, or even just a counter. So organize the counter so that we can count the number of times we get this success. And that's it. We're ready. That's all that we need to tackle incredibly complicated probability problems. And the only complication is going to be telling the story. Everything else is going to be pretty much the same each time. So let's take an example. The example that we're going to start with, well, we could start with rolling a dice, but that's maybe too easy. So let's jump into something a little bit more complicated. And this is the example that I did with the DDI guys. So this is the example that you've seen before. And it's called the birthday paradox. It's an extremely common probability problem that most people wouldn't be able to think through, but most people maybe have heard of it. It's not a paradox at all. I don't know why they call it that. But the birthday paradox, and we are going to solve it. Now, other people have solved it using the analytical approach. So if you're at a computer, and I guess most of you are, if you type in birthday paradox calculator, one of the top ones that will appear, I think, is from Math World, Click on it and keep it in the background, and we're going to compare our answer with the analytical approach. And we'll see if we get exactly the same. Spoiler alert, we wouldn't expect it to be exactly the same, but we would expect it to be very, very close. Now, what is the birthday paradox? Right, so the situation that we have is there's a bus. There's a bus driving past, and there are 23 people on the bus. So we've got 23 people driving past. What we want to do is estimate the probability that two people, any two people or more, on the bus share a birthday. So 23 people, do two or more of them share a birthday? And we want to estimate that probability. Now, why is there a bus? What does that matter? Well, it does matter, but we'll talk about that in a minute. But for now, we're going to assume it doesn't matter, but we'll worry about fancy bits later. So what is our story? Our story is the bus is driving past, we say stop the bus, then we go on and we ask everybody what their birthday is, and we write them all down, and then we get off the bus and we look, did we get two people or more with a birthday? It's the same. And if we did, we want to count that. And if we didn't, we don't want to count it. And that is the story. And then we will put that in a loop. So let's start with coding that story. What do we need to do? Right. All that we need to do is simulate 23 people and give each of them a birthday. That's super, super easy. There's a number of functions that are built into R that we can use to do this sort of thing. And if you remember, we're just going to take a pause and we're going to remember back to computers in business and maybe some of your tax modules and other things. You will have used a spreadsheet. And as part of that spreadsheet use, you will have used a function. When you see the word function in computing, it always means the same thing. And they're usually used exactly the same way. A function returns a value. That's what it does. So the classic example when you're using Microsoft Excel, probably the first one you used was the sum function. So equals sum, and then you open some brackets, and you give it some cells, and you close the brackets. Sum returns a value. The value that it returns is the sum of the stuff that's in the brackets. So the fancy name for the things in the brackets, that's the parameter list. That's the data that the function needs in order to do its calculation and return the value. So equals sum, open brackets, parameter list, close brackets. And it's exactly the same in R and many other programming environments, programming like other spreadsheets, other programming languages, whatever. The function that we are going to use for this is called sample. Now, what does sample do? So remember, first of all, anytime you have a function name, you need brackets beside it. And inside the brackets goes the stuff that the function needs to do its thing. Right, function essentially creates a box. Creates a box just like this one. I'm waving it because I don't know if this camera comes down here. But all I've got is a box. And then inside the brackets, the first parameter is the stuff that we want to put inside the box. So in this example, I've got the numbers 1 to 10. 1 to 10, and I'm just going to put them inside the box. What the sample function does, essentially, is it gets the computer to go up to the box, close its eyes, reach in, and lift out one of the numbers, if I can grab it. And I get the number 2. And then if we run the sample again, we close our eyes again, we reach in, and we get something else this time. It's a number 3. I haven't mixed these up very well, obviously. That's what the sample function does. Now, how can we use the sample function to simulate our bus? Well, all we need to do is to put the numbers 1 to 365 into our box to represent the days of the year. What about leap years? Well, we'll worry about that later. It's dead easy to include leap years, but we'll worry about that later. For now, let's just get the basics working. So 1 to 365 inside the box, and then every time we run the sample, the computer closes its eyes and pulls out 1. And we want to run this sample 23 times. Now, if you notice, the 2 that I took out before are still out. What we really need to do each time we take a sample is put them back. If we don't put them back, then we'll never get a match. We will go over that a few times, so don't worry about that if that doesn't make immediate sense. Okay, so inside our box, we want to put the numbers 1 to 365. You can do it like that. I'm not going to do it like that. I mean, again, don't write in. The way I'm doing it is not the most efficient way. I don't care. I'm not thinking about efficiency. I'm thinking about reusing it in the future. So what I'm actually going to do is I'm going to put a C there, a lowercase c. It stands for concatenate. And concatenate, the C, is itself a function, so we need brackets. And all that does is turn the numbers 1 to 365 into a list. In R, it's called a vector. You don't need to know that. Don't worry about that. So with that, C, open brackets, 1 to 365, all I've done is I've put the numbers 1 to 365 inside our box. Okay. Now, if you remember, back to Microsoft Excel, if you've got more than one parameter, you put a comma in between them, and it's exactly the same here. So our first parameter is what goes inside the box. Our second parameter is how many things we want to take out of the box. There are 23 people on the bus, so we want to take out 23. Each time we simulate a person with a birthday, we need to put the number back in. We do that with another parameter, and it's called the replace parameter. So all we're going to do is say replace equals true. So hopefully that makes sense, but all it's doing is when we take a number out, we put it back inside the box. And that's it. That's it. That's all we need to simulate one bus. Let's try it. Let's give it a go. So all I'm going to do is copy that. Usually what happens is there's a mistake and we have to fix it, but that's fine. We can live with that. And there they are. There are the 23 people that we have just simulated. How easy was that? Now, a quick glance, can you see, have we got any matches? I can't see, I can't look at that. But anyway, you can see if we've got a match or not, I don't know. But that's the bones of our simulation. Let's see if we can now improve it. Right. If you remember, back to Microsoft Excel, it was equals sum opens brackets. And that's what we're going to do here as well. We're going to say something equals sample. So we're going to give it a name, essentially. That's all we're going to do. So in Microsoft Excel, it was the cell equals sum brackets. Here, we're just going to give it a name. So we could call it birthdays. I'm lazy, so I'm just going to call it B-days. So in here, B-days equals sample blah, 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 blah. And you can use an equals sign, but for some reason, the R community tends to do that instead. It's a less than sign followed by a minus sign. It's like an arrow towards birthdays. So birthdays is equal to the stuff on the other side of the arrow. Okay, that's going to be our birthdays. Okay, then all we need to do is tell whether or not we've got a match. How do we do that? Guess what? There's a function for this. And I'm going to use the table function. So table B-days. And table B-days, well, you'll see what it does in a minute. If I copy paste that into R, Did I get my table? Let's do that again. Table B days. Oh, that is. Oh, excuse me, that is it, of course. Okay, so what I'm looking at here is this table that has been produced, and what it's saying is that birthday number 8 has been assigned once, birthday number 12 has been assigned once, birthday number 17 has been assigned once, etc., etc. And actually, look, we do have a 2, because number 48 has been assigned twice. There we go. So the table function is a quick way of visually seeing whether or not we have any matches. So let's have a look. B days, hang on, table, B days. Can we just say, are there any that are greater than 1? Yes, we can. So by putting in greater than 1, it tells us for each of the birthdays that have been assigned whether or not it's true that there's a match. And we've got 1 there. We've got 1 true in the middle there. Now, if you're playing along at home, you won't have the same numbers and you might not have a match. That is because we are generating random numbers and you are generating different random numbers from me. Okay. Table 1 birthdays is greater than 1. What can we do now? Well, we need to get the computer to tell us whether or not we've got any matches. There's no point us looking at it because that won't save us any time. Eventually we want the computer to do this all itself. I think there might be an any function. Any. Let me just try this first. No, that's not going to work. Let's try which. Any is obviously from a different programming language. I'm getting muddled. It's from NetLogo. I know it is actually. Oops, sorry, hang on. I should have done this before. Okay, there. I don't need the equals true. I just need any. So any table birthday is greater than 1, and it's saying yes, there are. And that's it. That's my counter trigger, if you like. So let's copy paste that back into my code. In fact, I'll just type it in again. Let's give that a name. Birthday tab. So the birthday table equals that. Any B tab greater than 1. That's it. And I can copy paste those 3 lines repeatedly into R and just see what I get. So you can see I've got a random selection there. Some are true and some are false. So sometimes I get a match and sometimes I don't. The story bit is working. So I am here. I have told the story once. Okay, is there a success we need to count? Right. In order to count, we need another function, and it's the if function, and you will have met the if function in Microsoft Excel as well. So I'm not expecting this to be complicated, but essentially what we're going to do is in front of that any is we're going to say if, open brackets because it's a function, and close brackets there. So it's going to look like that. It's starting to get more complex, but only because of the brackets. We've got loads of brackets opening and closing all over the place. If any birthday table are greater than 1, what do we want to do? We want to add them up. We want to count them. We want to include that as part of a counter. So how do we do that? Well, the way we do that in R, which is this bit is slightly different from Excel, is use curly brackets. So again, we're adding to the complexity, but it's just a different style of brackets. And what happens is, whatever I put inside those curly brackets will happen if that condition is true. And all I want to happen there is counter equals counter plus 1. Now, if you're not familiar with that, all that is going to do is increment a counter. So if the counter is 5 and we find a match, the 5 is going to become 6. If the counter is 5 and we don't have a match, it's going to stay as 5. And that's it. I think that's us. All we have to do now is loop the thing. Okay. So up here, we've got start the loop. So we know where to start the loop. Guess what? There's a function to do a loop. And it is the for function. So the name of the function, open brackets, and then inside the brackets you tell it the stuff that it needs in order to do its business. And the stuff in the brackets here is just the number of times we want to loop. And the way I'm going to do that is I'm going to say for I in 1, 2, with the semicolon, the colon, excuse me, means 2. And then specify the number of iterations, the number of times you want to loop, which I will just refer to as n. What does n mean? We haven't decided yet. That's the bit at the top. Organize the number of times we want to loop. I like it to be a lowercase I, so I'm going to go back and fix that. And then I need to open up curly brackets, and everything inside this set of curly brackets is what's going to loop over and over and over again. So that's my opening curly brackets. Where do my curly brackets stop? Well, I've got it down here. It says end loop. So down here, underneath end loop, or around end loop, you could do it before, it doesn't matter. Close your curly brackets. Okay, let's go up here. Number of times we loop, we've called that n. So n equals, and let's say, turn on number, 10,000. That's a big number. We could do it 1,000,000 times if you want. You could do it 10 million times if you want. And the more times we do it, the more accurate our estimate is going to be. So that's that bit. And then organize counter. All that means is we have to tell the computer that we have a counter. And all I'm going to say is counter equals 0. So up there, counter equals 0, and that tells the computer it needs to set aside a bit of memory for counter. Okay, so anybody at home who has opened up MathWorld's calculator thing, the birthday paradox calculator, go on to it, and it will tell you, it will ask you how many things are there. In our case, there's 23. How many people are there? And in our case, there's 23. And if you hit calculate, it will calculate the probability that if you've got a bus of 23 people, there's a birthday match. And in the comments, you can tell us what the answer is. And all I'm going to do is copy paste my code. And like I said, when I do this, usually there's an error. I've usually messed up the brackets. I will fix that if there is an error. And it didn't look like there was an error. Now I haven't got my result yet because I haven't done this bit down here. So calculate probability. All that is going to be is the counter divided by the number of times we did this, which was n. Okay, have we got an answer in the chat? I can't see the chat from where I am, but I'm going to give you my answer. Counter divided by n, 0.5. It rounds to 0.5. So there's a 50% chance, according to this, that on that bus there's going to be 2 people that share a birthday. Did anybody put an answer in? Nobody put an answer in. There are people online, aren't there? Okay. All right, well, I'll do it myself then. So if I go to Microsoft Chrome, not Microsoft Chrome, excuse me, what am I talking about? If I go to Google Chrome and type in birthday, BIRTHPARADOX, calculator, there it is, and look for MathWorld, Wolfram Alpha, that's what I wanted, Wolfram Alpha. And, oh, how did it know 23? How did it know that? How could it possibly, I don't know. So I must have done this in my DDI class, and somehow when I logged into Windows, it's remembered I didn't log into Windows. I didn't. I used. How did it know that? Anyway, at least 2 the same. There it is. There, 0.5. Exactly right. I'm taking a moment here just to take a breath because I want you to appreciate how amazing that is. We have mastered probability in less than half an hour. Well, have we mastered it? Let's try it. Let's try 11 people. So according to this, 11 people, it's 0.14. So let's see with our estimate, if we change the 23 to 11, leave everything else as it is, copy, paste in, copy, paste, boom. What was it? Counter divided by n, 0.14. 0.14. Wow, that is astonishing. That is extremely powerful. What we have just done is extremely powerful. And I hope you realize that. Now, what about leap years? We said we were going to deal with leap years. Well, to deal with leap years, all we have to do is change this bit from 1 to 365 to some other way of capturing the idea of an extra day every 4 years. What I would probably do, the laziest and the quickest and the easiest way, is to put in 4 years, and one of the years is 1 to 366. So how would I do that? I'll show you just because it's super easy. So I'm just going to put in some space there. So in this bit here, what I could do, instead of having 1 year, is have 4 years and change one of the years to 366. So if it mattered to you, and it won't, it's not going to make any difference whatsoever, the leap year. But if it mattered to you, that's how you would do it. Super, super easy. Now, I also said at the start that the bus mattered. The bus matters. Well, obviously. Well, I say obviously. I mean, it might be that in real life that the bus matters when you go out into Nottingham city centre. But in Nottingham centre, the bus probably doesn't matter. But if, for example, the bus has just driven past the astrology centre, and this week is Pisces Appreciation Week, the implication is that there's going to be more people on that bus with a birthday in March than any other day. Now, good luck getting Wolfram Alpha, or whatever it's called, that thing, to recognize this bias. You're stuck if you're using that as your calculator. And good luck if you're using other approaches, because if this is maybe a complication. Well, I mean, you could do it, but I don't know how you would do it. But with our approach, all that we have to do is in here, in this bit in here, specify that the days of March are more likely. So if they're twice as likely, you would put them in twice. You would put in whatever days represent March twice. If it was 4 times as likely, I would just put them in there 4 times. That would be the easiest and quickest way of doing this. Now, how would you know that? Well, you'd have to you'd have to go out and observe the bus stop outside the astrology centre. But the point I'm trying to make, this is the point I'm trying to make, that with the tell the story approach, the story can be as complicated as you can make it. The complication is in your ability to code it. Whereas with the analytical approach, if you look at people who have used analytical approaches, they very often say they simplify this, that, and the other to make the problem tractable. That's the word they use. In other words, simple. Simpler. We don't have to do that. So I want to just pause again and let you appreciate how powerful this is. With the ability to generate random numbers, we can solve probability problems.